Hello everyone. Let's keep talking about the Halliday and Resnick book, 10th edition, chapter 22, Electric Fields. I'm going to do my best to do problem number 32 on film. As we said, at the end of each and every video, all the problems for that particular chapter will scroll down the screen or scroll across the screen, whatever. They'll be on the screen. You'll have every single one of the problems showing up that were solved for a particular chapter. All those problems will show up, including the one that's being done here on film and all the other ones as well that are not being done on film. So I'm going to try to do about one problem per chapter of those 11 chapters, chapters 22 through 32. Those 11 chapters, about one problem per chapter is what the plan is right now from the Halliday and Resnick book, 10th edition. We are on chapter 22. Let's look at problem number 32. Problem number 32 from chapter 22. So problem number 32, they've got actually, I think the easiest way to do this rather than, the reading of it is good, there's nothing wrong with that, but let me try to just draw this thing out a little bit. An idea what we're talking about here. Not a great drawing here, guys, but there's a positively charged rod here. And there's a lot of ways we can kind of look at how to solve this, depending on the question that's being asked of us. Is it infinitely long? What is it? What's going on here? Well, in this case, it's not infinitely long, though we could, by extension, look at something that's very long and try to get an idea, and perhaps when we do calculus, perhaps things will go to a limit for us, as they often do. So in this case, they're not going in that direction, so we're not going to worry about it too much. The positive y-axis is up, negative y-axis is down. Positive x-axis is to the right, starting right here, x equals 0 going this way, and that over here. And you're trying to find, regarding electric fields, a number of things here. There's a positive charge, Q equals 7.81 picocoulombs, is spread uniformly along a thin non-conducting rod of length capital L equals 14.5 centimeters. What are A and B? And what are the questions regarding A and B? What are the A, the magnitude, and B, the direction, relative to the positive direction of the x-axis of the electric field produced at point P at a distance, capital R is 6 centimeters from the rod along its perpendicular bisector. So it's right down the middle. This thing is hitting the perpendicular bisector of capital L. And again, we could theoretically look at a lot of things. And maybe that's down the road a little bit. Let's see what we're going to do if we have to do something like that on the fly. But right now, this is what we're looking at. What is the electric field being experienced here? Well, I'll tell you what. The electric field, there's a lot of symmetry here because this y-axis bisects this particular non-conducting rod. It bisects it, completely bisects it. It's perpendicular to it, and it's a perpendicular bisector to it. What does that mean? Well, it means a number of things. The way it is, we shall see that all the horizontal components of the y field will cancel because of symmetry, and because of symmetry, we can also just look at half the rod and figure out what's going on here. Because there's symmetry here, guys, there is, let me just see how I drew it. Let me try to stay consistent with how I've maybe drawn it. Go back and forth on this thing a little bit. You got at some kind of general point here, guys, you got okay, let me just kind of bring this down to here. This is x equals 0 right here. Y is at a height of r. It's not going to be the greatest drawing in the world, guys, but it doesn't have to be either. You got something doing this, and you got, just by virtue of the symmetry of the rod, you got another something somewhere else doing the exact same thing, but just going that way. The y components, every place here, I can draw a vector representing an E field, a differential E field. I can also find a corresponding place where there's a differential E field where we've got the E fields crossing like this and the y components canceling out. I'm sorry, the x components canceling out, the y components adding up rather. So, I mean, we're assuming here same exact size, same exact symmetry. Well, there's a component this way, there's a component that way. Yeah, they cancel out. And then you got the y component of this guy, and you got the y component of this guy. So they're gonna, you better double it. Well, I got an idea. Well, I mean, they end up doubling up. If I just look at from x equals 0 all the way to L over 2, because the whole thing is L long, if this is L over 2, from x equals 0 to L over 2, if I'm kind of doing something this way and finding out how it's actually working, how big something like this is, when I get the answer, whatever answer I get for the integral, just double it, because there's always a symmetric counterpart on the other side of the rod that's been bisected. That's kind of how it goes. Having said that, I mean, let's say a few things, and I think we're okay. Some of this, like I said, I'll leave it to some of the written work that's already on there, but let's see what we can say regarding something like this. You're looking at this, and you can call lambda lambda is the linear charge density, total charge Q over a length L. What does that mean? Well, plain and simple, that means Q equals lambda times L. If you go dq dl on this one, you get, because of the uniformity of the distribution, here's the function, go dq dl of this function, you get lambda. dq is lambda dl. dl and dx are the same thing. Same, they're going along the same line as each other, so you can kind of go along those lines. So you can kind of just keep that in mind when you're doing this stuff, guys. We talked about the symmetry of the situation here. There's a lot to be said even there. A lot more to be said even regarding that. This right here, that's theta, that's also theta. From what we know, if this is theta, regarding this, that's theta here. If this is theta, that's theta there. X is equal to 0, and right here, x is equal to L over 2. So that's kind of the process that we're looking at when we're doing this thing. There's a lot to be said here. I mean, I said this in a number of ways. Perhaps there was a more efficient way to have done it in the written portion of it, but I think still it's, if it's anything, I believe it's relatively comprehensive, so I think it's going to give us some kind of gut feeling as to where to go with this thing. All right, so we got a lot here. Know this, you can always go back with the film regarding this stuff. Let's talk about a few things and see what we can say here. So if that's the case here, dq is lambda dl is lambda dx. So we know that. Let's go with this, since we're going to be integrating with respect to x, or at least very likely going to go in that direction. And like I said, a lot of this is going to get erased, guys. You can always go back. You've got that feature with the film, the one advantage we got regarding all this. and we can see what we could say here. What's going on here, guys? What we had over here was, there is this guy right here, that's epsilon. I'm sorry, forgive me, that's theta. This is theta, this is 90 minus theta. That's theta, this is 90 minus theta. Okay, this is theta, this is 90 minus theta. This is theta, this is 90 minus theta, making it perpendicular. Theta, this is 90 minus theta, this is 90. 90 plus 90 minus theta plus theta. This guy right here. Theta's right here, theta's right here. If this is theta right here, then you got theta right there. Well, what's so important about that? For example, it doesn't matter which one you go to here, guys. You can go to this one or that one. This is a differential electric field. DE. Okay? This is also, this right here is the DE. This is DEY. And if this thing right here is theta, up here it's theta. Same thing right here, guys. If this is EY or DEY, and this is DE, you're probably, take a snapshot of it. Doesn't matter which one you use, guys. It really doesn't. Let's use this one since we're going that way, but it doesn't really matter. If you got this, we talked about a lot of stuff. I mean, so we ended up having theta like this. Let me actually put this somewhere else, guys, just for the sake of kind of looking at it. I want to make this relatively large. Let's kind of do something with this, and just trying to debate with myself which way to go here. Let's just take this. And if that's theta right there, we've got, let me just draw it like this. The best way I can draw it relatively big and not clutter the whole thing here, guys. This is theta, this is DE, this is DEY. And this is the DE coming up this way. That's this thing right here, guys, which I've managed to make into a complete mess. But you saw how it looked initially. And this is all of this right here. If this is theta right here, this is 90 minus theta right here. This is 90, and right here, that's theta, right here. So here's theta, here's 90 minus theta, here's 90, here's this. What's going on here? DEY, DE, DEY divided by DE is the cosine of theta. So DEY divided by DE is the cosine of theta. So that's pretty interesting. Yeah, it's definitely pretty interesting. So what we have here is the cosine of theta. Yeah, is there another way we can kind of get a gut feeling for what the heck's going on with that? Yeah, this cosine of theta. Here's theta. To get the cosine of theta, this is length r, this is length, and if this is x right here, if this is r and this is x, this is the square root of the quantity r squared plus x squared. Here's the hypotenuse. The square root of the sum, r squared plus x squared. This is the length of that leg. This right here, capital R, divided by the square root of the sum, capital R squared plus x squared. Capital R divided by the square root of the sum, r squared, capital R squared plus x squared. That ratio, r divided by the hypotenuse, is cosine theta. We already said that was also equal to this. DEY divided by DE, which is equal to Absolutely. Absolutely true. So, I guess there's things we can say. I mean, we've said a good amount. Let me erase some of this. We've got, again, you've got access to this through simply reversing the film. If we want to go back a little bit to some we're doing here. But let's see what we can say. See what we can say and maybe cannot say maybe. Let me still leave a few things up here, guys. We already did this. I can move this out of here. Okay. Got what we got here, guys. Let's talk a little bit more as we proceed with this. So we can also, now, okay, so what? What's the big deal? Well, we said this right here, which means we can write DEY is equal to DE cosine theta. And okay, yeah, that's certainly believable. What's DE? Well, DE is K times Q, or actually DQ, right? The differential amount of charge, K dQ, that's like the KQ, divided by small r squared. Small r squared is the length of the hypotenuse, the length to get there. So small r is the square root of r squared plus x squared, the whole thing squared, times the cosine of theta, and the cosine of theta is r over the square root of, and I'm going to write this again. I don't like writing this low on the board sometimes. I'm sure you can probably see it, but let's just write that again because it's a very vital point. I think it is. DEY equals DE cosine theta. We already said that. What the heck? Let's say it again. DEY equals DE cosine theta. DE, we said was, I just think it's a little more clear, guys, when it's written in the center of the board like that, is the length of the hypotenuse, correct, squared, that's your r squared. If r is this, the r squared at the bottom is going to be r squared plus x squared. So that's what that is. Cosine of theta is r over the square root of the hypotenuse. This right here is the hypotenuse squared, and this is the square root of the hypotenuse. Wait a minute. Hypotenuse squared times the square root of the hypotenuse is the hypotenuse taken to the third power. In other words, the square root of the quantity, capital R squared plus x squared, taken to the third power. So let's see what we got here, guys. At the end of the day, what's going on here? We'll see where the bread and butter is on this whole thing, guys. How you want to visualize what the heck just happened here, what we're doing. Well, this right here is the same as, you see it, you're looking at it, guys. So many ways to go with this thing, the whole process here. This is, how do you want to say this? Okay, you're looking at what I did right here. You saw the setup of it. I'll tell you what I'm going to do. Square root of that is to the 1/2. The square root of this, the square root of all this is that thing to the 1/2 being squared. The whole thing squared. Yeah, the square root of that squared. If you exponentiate an exponentiated quantity, you multiply the exponents. That's to the 2 over 2 power. That's just the hypotenuse itself. Yeah, I don't want to write it that way. I mean, you're right, it is just the hypotenuse itself. If anybody's going to say that, I agree with you. I'm going to call it 2 over 2. If you multiply two exponentiated quantities that have a common base, you're adding the exponents. So what does that mean? Well, if you're adding the exponents, you end up getting what's 2 over 2 plus 1 over 2? Let me just make sure we got it right. Okay. And we said we got the KQ, KDQR. So dq kr, there's a whole bunch of ways you can go here. dq times kr. I'll probably write that again too, man. There's a little bit of a... So let's take a look here. I mean, this is kind of where it's going. Let's erase a few things and see what we can do regarding this. And again, this is a little more... And there's certainly other ways to look at it, but I think this somewhat lengthier approach is kind of gives us a real intuitive feeling for what it is that we're trying to do here, guys. So you see what's going on. So we got that. So let's kind of get down to the business of it, guys. KR dq, I mean, it's kind of a horse apiece how you're going to go here, guys. Here's KR dq here. Big thing is have the big picture under control. It's a big conclusion. And from here, I guess there's still a number of games we have to play. But if we can reach a conclusion like this, it's pretty important. Something pretty important as we get along our path. Now again, didn't we say, guys, that dq, see, we're trying to make this in terms of, I got so many variables going on in here. This is all true. There's nothing wrong with any of the logic that we brought forward. Nothing wrong with it at all. But what's really important is, okay, I've got all these differentials here, okay, everything's great. Let's try to make things line up with what variables are present. R is a constant, it's not a variable. K is a constant, not a variable. So K and R are constants. R is a constant, X is a variable. Is dq something can be expressed in terms of dx, in terms of some differential of x? Sure, dq is lambda dx. If dq is lambda dx, if dq is lambda dx, let's write it down. And I got it written down different ways in the book, but that's huge. Well, this is what we're doing. This is what we got to have under control if we're going to figure out what's happening. We're looking at this. If we integrate this, we already canceled all the delta x's. Forgive me, the dy's, the dx's. Forgive me for not being able to speak, guys. Let's do it one more time. The dex's, the dex here, the dex here, cancel. All the dex's are canceled. All the deys occur twice. So if I just find it on one side of the the non-conducting rod. If I find it on one side of the non-conducting rod, what the DEY is, if I double it, it's as though I found it for both sides. What happens on one side, regarding one side, happens regarding the other side as well, identically in terms of magnitude. There's going to be a cancellation because of the symmetry. The DEX and the DEX always will be canceling out. And then the DEY will add together. Well, let me just get one DEY and then double it. Well, I'll just do it by doing one side of that non-conducting rod and figure out what's going on here. All right. Let's make sure I'm kind of on the right path on this one, guys. I want to make sure I can. I mean, some of these are a little more like the written word on regarding the whole matter is a little more wordy. Potentially a little more wordy on this whole process, but let's see what we got. I think what we're doing is there's a number of ways to go, and a number of ways you could probably get the answer, including integral tables. I mean, if you look at an integral table regarding a particular form of an integral, they'll have the answer for you. But let's be a little more let's be a little more old school about the whole process too. I mean, that's certainly an option. But let's be a little more old school about the process, a little more, I think, for our personal enrichment, looking at the mathematics as it could play out. All right, so let's erase a number of things here, guys. We've got what we got. You know how to look this stuff up, and we will take it from there. We have what we need. We've got an idea what the problem is. Now, solving the problem is, I mean, we can really state what the problem is pretty strongly and know what we have to do. We know what the problem is and we know what we need to do. How easy is it to do? That's potentially a debatable question. Well, let's see here. It's all going to be, you know, like I said, at the end of the day, we know this is going to be that EY, we're just going to go from 0 to L over 2. L being a finite number. Be an interesting scenario if we made the L infinitely long. Is there a limit? Now, they're not asking us that. They're not asking us that. They're not asking the things infinitely long. I'm saying it's from 0 to L over 2. You're doing this. What did we write down earlier? You're actually finding just 1/2 of it and then doubling it, as we said. Well, why don't you take the KR lambda out of there, all constant, multiply 3 constants together, you get another constant. Multiply a 4th constant called 2, you still got a constant. Well, aesthetically, this is somewhat, and I'm sure there's integral tables that can give us this. We're going to opt to be a little more rigorous about the whole process. All right, well, yeah, I mean, it goes as it goes, guys. I mean, we've got a whole bunch we can do. Trying to think how I did a little bit of the setup here, guys. I want to kind of do a setup here and then time out a little bit and figure out where we're going to go. Okay, I think this is fine, the way we're proceeding. Okay, guys. So we look at this. Let me just see here, guys, where we are about. We got this. Let me keep walking with it the way we got it. I mean, and it's debatable how many steps you want to take. I think I'm erring more on the side of caution than is necessary, than is maybe something that is necessary, but the side of caution is what we're erring on, I guess. What do we got here? Well, we got EY. Is lambda the same as Q over L? Absolutely. Lambda is the same as Q over L. R is R. Let me just try to give us a little more room, guys. When you write as large as I do, you need a lot of room, I guess, but let's deal with this a little bit. Bear with me a little bit, guys. It's very hot in here, and I'm taking breaks a little bit to get a little something to drink here. We've just had some storms and it's very humid, so it's I'm not sure what the air quality is, but so just bear with me here, guys. I don't want to trash the board by getting it too wet or anything like that. Okay, so as we look at this, see what I can say here. There's a 2 here. K, okay, let's do a bunch of things here. K is 1 over 4 pi epsilon naught. 2 times 1 over 4 pi epsilon naught is 1 over 2 pi epsilon naught. Lambda is Q over L, and R is R. True. That is absolutely true. So, okay, now what do you want to do? Well, a lot of ways to argue this, guys. Yeah, okay, true statement. Not a big deal. Seeing a lot of the same stuff here, guys. The big move here is, guys, if you're going to talk about pi, if you're going to talk about K is 1 over 4 pi epsilon naught. 2 times 1 over 4 pi epsilon naught. 2 times 1 over 4 pi epsilon naught is 1 over 2 pi epsilon naught. Lambda is Q over L. The R is here. You got this. Then we make kind of an interesting move. I'll make kind of an interesting move here, guys. Why don't you take and go for this right here? Why don't you, let me kind of just make the move sort of right now. Is this a true story? R squared over R squared. Yeah, R squared over R squared is 1. Not a big deal, okay? And some people would say, so what? What's your big deal here? I'm going to pull the quantity R squared plus X squared. The quantity R squared plus X squared to the 1/2 is present right here. I'm going to pull it out of here, leaving the quantity R squared plus X squared to the 2 over 2. And then the quantity R squared plus X squared to the 1/2 has been pulled out this way, all of this remaining in the denominator. And I got R squared over R squared. I'm going to take this R and bring it in there, and you're going to see what's about to happen. 2 pi epsilon naught So far, so good. Let me give us a little more room. Pulled that out of there. I took this R, brought it in, took the bottom thing here, left it on, took part of the bottom thing here, left the part of the bottom thing here, left everything on the bottom, but pulled some of it out. The R squared plus X squared to the 1/2. So we got this, R squared plus X squared. And guys, like I said, I'm sweating like crazy right now, so I don't want to be touching the board too much and mess it up. So forgive me for running around. I probably got to take a water break soon again. We've got, let's try it again. There's a dx here. There's a dx here. Keep that way on the tail end of this whole thing. So there's the dx. Way out there. The R squared, leave it alone for now. You'll see what I'm doing in a little bit. Got all this. That R came in. You pulled out the quantity capital R squared plus X squared to the 1/2, and that left the quantity capital R squared plus X squared to the 2/2, to the 2/2. You add 2/2 and 1/2, you get the 3/2, and we were already talking about that earlier. Let's have that one pulled out, guys. To the 1/2, and I brought the R in from right here. From right here, I brought that R into here as well. So you had R squared over R squared, and there's an R right here. Bring that R, so you got R cubed over R squared. Well, R cubed over R squared is just R. That's what we had over here anyway. But there's a reason for this. What do you got? The other one's 2/2. That's left over, so you end up getting R squared over R squared plus X squared to the 1/2 squared, which is the square of the hypotenuse. And that's multiplication here. And this is 1/R squared. People are still wondering, obviously, and rightfully so wondering. So what? What are you seeing here? You know, what's of interest? Well, you can keep doing this, and at least if you're not going to directly solve the problem just yet, get a visualization of some of the mathematics that's present. This is 0 to L/2. And you got, well, what do you have? I mean, you got this, and I guess you can really look at the whole thing here. Here's your R cubed again. R cubed, that's the square root of this squared. This is just the square root of this. Square root of this to the second power, the square root of this to the first power. First power plus second power is third power of the square root. So what you got is yeah. What is this? This is basically the R over the square root of all this. This quantity is the same as this quantity cubed. This over the square root of all this, if you were to take this over the square root of all this, which is the cosine of theta, by the way, this over the square root of all this cubed gives you this. So there's a visualization here. There's something we can visualize. I mean, you look at it, we see where it's at. There's a lot of ways to do it. Again, I'm kind of debating where to go, how to actually go with this. All right. Well, what I just say? What I basically said, EY at the end of the day is going to be Q over L, which is lambda, by the way, over 2 pi epsilon naught r squared 0 L over 2. It's basically just this. See, what I did was, you can take the r squared here on the bottom, the 1 over r squared, and bring it out. It's a constant. 1 over r squared, bring it out, bring it to here. That's what got me here. Again, I just said that all of this is equal to the cosine of theta cubed. All of this is the cosine of theta. All of this, the entire ratio cubed, gives you that, believe it or not. Look at it, we see that it's true. And there it is. That's kind of where we're going. Well, okay, you know, maybe that's not as intimidating as this integral earlier on. Perhaps it's not as intimidating if we perhaps write it in a different manner. If this right here is the cosine of theta, that's the cosine of theta. Is there something we can do here? In fact, there is. And here's where it gets really interesting. Okay, so you're seeing everything here, guys. You saw what I'm trying to say here. So there's the bread and butter of a lot of what's going to be happening here. Let me try to leave that up there. And like I said, we always have the option of going back a little bit. There it is. Okay, let's talk. I've already mentioned it. Let me be a little more explicit about the whole matter then, I guess you could say. Cosine of theta is r that's the adjacent over hypotenuse. That whole business right here is the hypotenuse. That's the adjacent. Adjacent over hypotenuse is the cosine of theta. based on what we've been talking about. That's the cosine, which implies rather obviously, if you cube it, or if you simply just cube the other one, that becomes oh, we've already seen that. Yeah, I just told you it was going to be cubed. So that's interesting. So let's see. There's got to be a way here. I mean, we're seeing this. We're seeing something that's relatively, I don't know, somewhat easy to look at. Now look, if you remember, you're going to start, here's the non-conducting rod. You're going to start here. We're going to double it, right? If theta is here, theta right here, straight up and down, theta is 0, and theta right here is something different. So theta is going to go from 0 to the inverse, It's going to be a lot of ways you can actually play this if you want to do it. So, but it's going to be, this is going to be theta equals 0 straight up and down, and this is going to be theta final. Some kind of theta final. So theta initial is 0, and there's going to be some sort of theta final and how it opens up. So we'll see how that's going to play out, how we're going to talk about that when we do it. We know this is R. This is R. This is R squared plus x squared to the 1/2. And this from 0 to here. Now, I don't know how long, we know how long it is now, but let's say this thing goes further. That's just in general. Let's say this thing is longer than that. It comes this way. This is no longer theta final. Theta final is some theta, let's say. Theta final is whatever it's going to be. Some theta final, and we'll figure out what exactly that's going to be. We'll cross each bridge as we got to go to it, guys. But for the theta here, this is x. This is this length. This is x. This is r. This is the hypotenuse. And can we kind of figure out a little game plan here? I'll tell you what I'm going to do. Why am I saying this? Because I'm going to have to make the conversion from dx to d theta if I think I can be clever enough to get around this thing, to see where we're going to go. So let's see what we do have. Okay, I said what I said. This is all true. There's nothing, none of us are debating this. We got this. We got this. We're doing well. So what are we going to do? Well, you got to be really careful here. They got this thing called dx right here. I am going to make a conversion and get away from dx, but the only way I can get away from dx is still stay faithful to the original integral. We'll call this the original integral. I still have to stay faithful to this original integral if I can actually solve this. This integral solves the problem. So I have to be faithful to it in my mathematics, in my approach, in my argument. This integral solves the problem. Well, I'll tell you what, do I got a way around it? Well, yeah, Q's a constant, L's a constant, 2 pi, epsilon, and capital R, they're all constants. So capital R squared is a constant, of course. So they're all constants all over the place, except for the x. X, there's an x squared here, there's a dx. I can do it. This can be done. This can be done, but let's get around it. Why don't we convert the limits of integration of 0 to L over 2 into something associated with theta? Why don't we convert dx into something equivalent to something associated with d theta? I'm not changing this integral. I got to make this very, very clear, you guys. This integral solves our problem. And it is this integral that we will use, but we will convert it to language involving theta. Interesting. Well, I guess there's an easy way and a hard way for this. Is there a way to write dx d theta? And I wrote it in different ways, but dx d theta. I mean, how much of a dx is there? How much a change is there in dx if there's a change in d theta? If you change d theta, you've got to use radians. Radians are the language. The language that we need to use has to refer to radians. Radians are the most natural discussion pertaining to angles and their relationship to the lengths and differences in sides. Sides and how their length changes and how trigonometric ratios occur with a change in theta are most naturally manifested, most easily manifested, most naturally manifested by considering radians as the lingua franca for angles. It's in terms of radians. So this is dx. There's a d theta here where that would have happened, et cetera, et cetera. Well, easier said than done, I guess you could say. Well, maybe not. Is it true? A lot of ways, a number of ways you could play it. How does dx happen? How does dx happen, my friends? Well, there's a change here associated with the change in that. What do you say? There's a number of ways here. Let me just make sure. There's a whole bunch of ways you could take it. Is it true? I guess I showed it a number of ways here. I'm arguing a little bit with myself how I'm going to approach this. Let me keep thinking about how I want to do this, guys. What I would do here is, if theta is theta, if theta is theta, the tangent of theta is x over r. This is theta. Opposite over adjacent is the tangent of theta. The tangent of theta is x over r. How it changes, you could kind of look at it and say, well, you can go d tan theta. D tan theta d theta is the rate of change of the tangent so there's a lot could be. Let me try to. I wrote it differently in different places, guys. I guess I could. I'm just arguing a bit with myself right now. Arguing a bit with myself right now on how I want to do this. I'm going a little bit off, somewhat differently than what I actually. The notes are fine the way I'm showing it. I may just want to say this. Let's say at least an approximation. Let me try to. Again, let me go a little bit away from the notes I presented, but the notes I presented are fine. There's not an issue there, guys. But let's say delta x over delta theta, let's say. Or let's just say, how could you get a delta x? And we'll say eventually if we make delta x small enough, it's approximately equal to dx. So, how are you going to do it? Well, I'll tell you what. Let's get a difference. There's a tangent theta theta final, or theta 2, and whatever the tangent is right here for theta 1, for theta 2. Theta 2 is bigger, let's say. It goes the bigger angle of theta for our purposes. If it's theta 2, tan theta 2, tan of theta, that's opposite over adjacent. Opposite over adjacent times adjacent will just give you the opposite, how long that is. So it's basically going to be this, guys. Again, forgive me for, you're looking at an x2 minus an x1. Sounds good to me. This one's longer. This one's down here. This is x2, this is x1, and this is your dx, or delta x. Kind of use them interchangeably. Let's say delta x for now. Let's just forget this, but you can use either way. Delta x, if this right here is x2, and this right here is x1. x1, x2, that's x1, that's x2. Okay. What does that mean? Well, how about the tan theta 2 times r minus the tan theta 1 times r? Okay, great. So what? Yeah. There's other way, and I did show this somewhat differently, and we'll talk about it, however much we need to talk about it. Here's r times tan theta 2 minus tan theta 1. Okay, so what? Well, okay, that's pretty significant. Because that right there, delta x is r delta tan theta. Everything's set up the right way. Okay. Divide by delta theta on both sides. Delta tan theta divided by delta theta. Multiply by delta theta on each side. You're probably wondering, what is he doing? What's the big deal? Delta theta times delta x delta theta equals r. Watch what I'm doing, guys. You just divided by delta theta. Why are you doing that? Because I'm going to leave the delta theta here and go delta theta there. What's going on here? What just happened here? Delta theta times delta x over delta theta times delta x over delta theta times delta x over delta theta is delta x. R this, r times delta tan theta over delta theta. Well, if you make the difference smaller and smaller and smaller, you're getting the derivative of the tan function with respect to theta. And if the differential is smaller and smaller and smaller, you saw what I did, guys. Luckily, we got the reverse feature if we need it. Fascinating. Answers a lot right there, actually. Again, this is delta theta times delta x over delta theta. R times delta tan theta over delta theta times delta theta. Yeah, just wrote the same thing here. If you take this smaller and smaller gradations of delta theta, this becomes d tan theta d theta. The delta theta is, for all practical purposes, d theta, and the delta x is dx. That solves it. That does a lot. You come to here, you know, you could say a bunch of things actually. You could say that delta x d theta divided by d theta on each side is r d tan theta d theta. So on and so forth. I mean, I expressed this fact. I expressed this fact somewhat differently in the notes, but it's the same exact fact. The logic is essentially identical. It's a different way of maybe making the argument. But this is what's going on. Pretty important stuff, guys. Once you get to here, I think we got our way out. What do you mean got our way out? Well, right here, delta x. Dx can be written as and there it is. And there it is. I mean, it works just like that, and that's how we have it. This is big. Once you get to, you multiply by d theta on each side. Leave the d theta here. You don't want to leave d tan theta and just leave it like that. D tan theta is really what it is at the end of the day, but let's have an expression for d tan theta in terms of d tan theta d theta times d theta. So you leave it like this. You multiply by d theta on each side. Yeah, that really does cancel out, and you got d tan theta. But d tan theta is the derivative of theta, is the derivative of the tan of theta with respect to theta times d theta. This is huge. And that's what you're going to use to get to where you're going to go, you guys. I guess a question that could be asked, and if you look at the setup on the whole thing, guys, so you got all this. So we're looking pretty good. We're looking all right. So we got a lot here, guys. Let me try to just arguing what to erase, what not to erase, I guess, at what juncture, right? But you can say a few things now. Now, what's going on here? Well, by the way, what is d tan theta? What is d tan theta d theta? D tan theta d theta is d sine theta over cosine theta. All of that, d theta, is what it is. This is the quotient rule. And again, this is all done with radians. This is the radian is the language, is the measuring, the great measuring stick for angles is the radian, and everything else is based on the radian. It's not often communicated, but that's what it is. It's really the way that it is. So you get to here. This is f. This is sine theta is the f function. Cosine theta is the g function. df over g is equal to g f prime minus g f prime minus f g prime over g squared. What's going on here? If you look at it, cosine times cosine, cosine theta times cosine theta is cosine squared theta. Sine theta times negative, forgive me, not that. Cosine theta times cosine theta is cosine squared theta. Cosine theta times cosine theta is cosine squared theta. Sine theta times negative sine theta is negative sine squared theta, minus negative sine squared theta. What's going on here? D tan theta d theta. D tan theta d theta. Cosine theta times cosine theta is cosine squared theta minus the quantity sine theta times the quantity negative sine theta. Sine theta times negative sine theta is negative sine squared theta minus a negative sine squared theta over cosine squared theta. Minus a minus is plus. Cosine squared theta plus sine squared theta is 1. There it is. That's 1 over the cosine is secant. 1 over the cosine is secant. That's secant squared. The derivative of tangent of theta with respect to theta is secant squared theta. This is a little more direct because at least you're referring to what it actually began with. You're referring to the sine function, cosine function, tan function, how it works. But that'd be the secant. That's secant squared, 1 over cosine squared theta. So there it is. So if that's the case, we got this guy right here. What do we got? Well, we got, guys. We got dx is r. I'm going right here, guys. I'm going right here. Dx is r, d tan theta, d theta, d theta. Dx equals r, d tan theta, d theta, d theta. That is yeah, it is that indeed. So you're looking at it, guys. You're looking at this. Put this dx in place of theta. Theta here, it starts here at 0 and it goes to the inverse tangent of where it goes for a length of L over 2 divided by, so theta sub I is going to be equal to 0 if we're going to do this in terms of thetas. Theta sub f is going to be the inverse tangent of r divided by L over 2. Forgive me, no, L over 2 divided by r, rather, I'm sorry. So it's going to be inverse tangent to find out what's going to be going on when you actually go that way. Look, big thing here, guys. Dx equals r, 1 over cosine squared theta d theta. I'm putting that right here. In addition to that, I'm calling this 1 over, forgive me, I'm calling this cosine theta cubed. See, so at the end of the day, you guys, let's see what we got here. I wrote a lot, and I'm going to end up erasing a lot here, guys. That's big. That's huge, so we're going to leave it. Where to stop, where to finish, guys. I don't want to erase any of it, but I don't have unlimited blackboard space, so you're going to have to come back. You saw a lot of what I wrote. Going on here? I'm sticking to this. E to the y is equal to q over L, which is the same over which is the same as q over L, which is the same as lambda. I mean, you can argue that either way. If you already got the lambda already figured out, just did the simple arithmetic related to it and go for it. I am going to integrate from 0 to the inverse tangent of L over 2 divided by R. That's theta equals 0 in terms of radians, and theta equals that. What's going on, guys? Didn't we say that all of this is the cosine of theta? If you cube it, you got the cosine of theta cubed. True. Didn't we say dx is this? Wow, this becomes manageable pretty quickly. E to the y becomes q over L. It's a ratio. R squared. Let me pull. See that R right here, guys? There's a capital R right here. Let me pull the capital R. Let me pull the capital R out from the integral. Take the capital R, pull it out from the integral, put it here. Capital R over R squared, just R on the bottom. So we got this. And then we got this. Let's not worry about the limits of integration just yet. Cosine squared theta goes into cosine cubed theta, just cosine theta amount of times. That's a simple integral. It was a nightmare to begin with. There was a lot of stuff going on to begin with for us to get this thing to go. But absolutely. I mean, we're here. All right, what is the integral of the cosine function? It's a sine function. Q over L. Okay. Wow, L could be really long, I guess. That's another topic that we can discuss. Sine theta. Now again, they gave us the data, guys, in the problem itself. They're telling us, you know, the length of L happens to be 14.5. The length, capital L, The length capital L in this problem is 14.5 centimeters. That's 0.145 meters. Q is 7.81 picocoulombs. And again, we'll put in all the appropriate numbers associated with that, what pico is. So nano-picos, that's 10 to the negative 12, it should be. So there's micro, nano, and pico. So 10 to the negative 6, 10 to the negative 9, 10 to the negative 12. So they got picocoulombs here. Q equals 7.81 times 10 to the negative 12 coulombs. That's 7.81 picocoulombs. Capital L is 14.5 centimeters. Capital L is 0.145 meters. Capital R is 6 centimeters. That's 0.06 meters, et cetera, et cetera. They gave us all the data. So from there, we can actually find the inverse tangent of L, the inverse tangent of L over 2 divided by R. When they gave us what L is, when they gave us what R is, we're there. We can find it. So you do the appropriate integration and you'll be fine regarding that. Pretty significant. I mean, once you get to here and just do the appropriate, obviously just do the appropriate limits here when you're doing that. From theta being 0, starting from theta equals 0, that we know, and then theta being the inverse tangent of the quantity capital L over 2 over R. Okay, so theta F here. That's pretty interesting. When we actually do it, wow, it's a very doable problem, I guess you could say. I guess after the fact, anything's pretty easy if we can actually get there. Notice how the trigonometry let us get to where we wanted to go. That's pretty interesting matter in its own right. For the record, definitely of interest. So that's it. You can go that route if you want, or you can simply, and we said what the inverse, and they gave us all the data that we need to actually be able to get these answers here. So when we're doing this, you're eventually going to put the inverse tangent of the quantity capital L over 2 over capital R. And that's the theta sub F. That's here. That's regarding that. And this is the theta sub initial under consideration. Couple things to kind of look at here. Can we write that in terms of that one right there? Well, what is the sine theta? The sine theta, you guys, the sine of theta, sine of theta, if this is R, and this is square root of that, or to the 1/2, however you want to write it, what's the sine of theta? For the record, the sine of theta is opposite over hypotenuse. That's the sine of theta. So what are you saying here? We're saying a lot of things here is what we're saying. You can this can be played a whole bunch of ways here, but at the end of the day, what is that? Well, you got to remember all of these, the R stayed, the R got out. Let me... Right, there was an R that came there and all of the other stuff here, guys. So, the way this integral can actually be done, this right here, put right here, will tell you a lot of stuff. This is true and you simply go for it. This whole song and dance at the end of all of it could just as easily be, well, it can be written now easy enough as it is, or easy enough to look at it, hopefully, to 2 pi epsilon naught, just the r, sine theta is x over r squared plus x squared, the whole thing to the 1/2. So, interesting point. I mean, very interesting point how the whole thing proceeds. They're equal with the right limits of integration and stuff like that right here. So I don't, we're getting, we got it right here. The thing is, it's a done deal. We got it there, guys. As you look at it, you saw me do this now, guys. Okay, so we got this right here, and just evaluate within the appropriate limits. For here, for the appropriate limits that you would get, you're starting at x equals 0, and you're going to go to L over 2. Wow, it's a lot easier to do. So you can evaluate here, or you can evaluate here, and you're getting the same answer. Makes sense to me, because L over 2 is the x value, the longest it gets. That's the hypotenuse. If you put L over 2 in here for x, it's L over 2 divided by the hypotenuse. That's sine theta on the big side. On the short side, the sine of theta is 0. And that makes sense. So that was 0 here too. At theta equals 0, the sine of 0 is 0. At theta f, it really is L over 2 put right here, L over 2 put right here, the quantity L over 2 squared, all this stuff, get that, you're good. You got all that, and so this right here is mathematically identical. Absolutely mathematically identical. This right here is mathematically identical to this. So it's your choice how you want to do it. You plug in there, guys, and you get the answer. I mean, the answer itself is, I don't want to say it's trivial. The process to get there is really the challenging part. It's really the challenging part that makes it of interest. I wrote it slightly differently in my notes, but again, and I'm going with what the instructor solution manual said on this, guys. Instructor solution manual, the magnitude of this is, and again, the main process here, guys, is the process. If you get this thing right, if you can actually set this thing up, you're doing good. There it is, according to the solution manual, as to how they got you plug in the answers. The answers are obviously very important. You want to get a specific answer, you want to get it right if you're doing some kind of engineering problem, obviously. But the process to get there is going to help you do it in all circumstances. Are you strong to be able to set up a process? Do we have the mathematical background to get this thing done? This thing is, EY is vertically upward, guys. Okay, great. I guess it really does beg the question. What is, and we could say, sine of theta was this. This is an interesting conclusion, guys. Fascinating conclusion, we can say. This right here. Constant, 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 constant. They're all constants. That's a constant. This right here, in all circumstances, if you put a 0 in for x, 0 divided by any non-zero number is 0. Really? That's the same as the sine of 0. The sine of 0 is 0. Sure it is, because the sine is x over this quantity right here taken to the 1/2 power. If you put a 0 in for x and a 0 here for x, this is just r squared. Square root of r squared is r. It's 0 over r. That's 0. L over 2 is right here. L over 2, the quantity L over 2 squared, the quantity L over 2 squared plus r squared is a particular number. Square root it, it's an answer bigger than L over 2. This is L over 2. L over 2 divided by something bigger than L over 2 divided by something bigger than L over 2 is a number less than 1. If this is L over 2 and this is L over 2, the quantity squared plus r squared, the square root of that is a number bigger than the square root of L squared over 2 squared. It's a number bigger than L over 2. L over 2 divided by something bigger than L over 2 is a number smaller than 1. But it's still a positive number and it still gives you an answer. When would this be at its maximum? If theta was 90 degrees, the only way you're going to get a 90-degree angle, only way you're getting a 90-degree angle with this guy is if you make it infinitely long. If you make it infinitely long, this thing starts coming close. It's not 90 degrees right here, guys. I'm just exaggerating it, but I'm saying it gets in the limit as L over 2 goes toward an infinitely big number, the theta sub f goes toward 90 degrees. The sine of 90 degrees is 1. If this is a really, really huge number, the x, which is some L over 2, which is really, really big, but let's say let's not call it L over 2, but it is L over 2. But it's a really long rod. Long non-conducting rod, very long non-conducting rod. How long? Oh, it goes to infinitely long, or very, very close to infinitely long. This is huge, and this is huge, but this guy's a constant. Remember, this guy's right here. Here's P. Here's the length R. There's the length R, you guys. Okay, that's the length R, and you got this right here, this right here, and that's P. So that's it. I mean, let's try to. Well, that's pretty big. It opens up pretty big here, guys. You know what? This thing's even longer than that. Opens up even more. Obviously, I'm not drawing this that well, but it's still not a 90-degree angle, but it's approaching it when we do something like that. Okay, so this is X. Okay, so this is R. That's X. Here's P. So, and again, you can see, guys, the further along, if it is a long path to take, this angle gets pretty big. You understand that if this is a real long walk this way, the X and this quantity right here to the 1/2 aren't too much different in length. This one's always going to be bigger, but it's not the same as like when you're here, here's R, and then you're here. This R squared plus X squared to the 1/2, that's sure a hell of a lot bigger than this X. But right here, this R squared plus X squared and this X and this R right here, they're not, you know, the further out we go, the closer the ratio of X over R squared plus X squared to the 1/2. The closer that this ratio goes toward 1. The bigger this angle theta gets, and it's going to go to 90, the bigger the angle theta gets, it's going to 90 degrees. The sine of 90 degrees approaches 1. The sine of 90 degrees approaches 1. So if this goes toward a very, very big number, we'll call it X, and a very, very big number squared, plus a number that's really not big at all compared to this very, very big number. When you add the two, this is just something a little bit bigger. You add the two, it's just something a little bit bigger than X squared, and when you get the square root of something a little bit bigger than X squared, it's just something a little bit bigger than X. And the further out you go, the closer the ratio comes to 1. In the limit, if you were to go to theta going to a 90 degree angle, which is pi over 2 radians, you always got to keep it in radians. If you go from theta equals 0, yeah, the straight up, you know, theta equals 0, the straight up and down, to theta goes to infinity, you know, from theta, you know, theta equals 0 to theta going to pi over 2 radians, you know, it's going all the way across there, guys. This theta 0, that's 0. Theta pi over 2, that's 1. You'll get just this for an answer at the end. If this was an infinitely long rod, you guys, there's your answer, period, for any length you want. In the discussion that we've given, for any length of the non-conducting rod, a rod made of non-conducting material, for any length that we are talking about regarding finding the E field at a point P, our distance away from, you know, our distance away, a perpendicular distance, our distance away from the non-conducting rod, if it's a very long rod and it's centered right at the perpendicular bisector, when you find the perpendicular distance down, that perpendicular distance, the segment along the line of the perpendicular distance, is a perpendicular bisector for that non-conducting rod. If you make the rod infinitely long or very, very, very long, that goes. And you got this. They didn't really go there with this particular problem, but we know that's the way it is. We know that's the way that it is. Okay, I mean, that's it. Let me make sure I'm not missing something on that. I think we're okay. We looked at, I mean, again, I showed it in the notes a number of ways, guys. I think you're going to be in pretty good shape if you look at my notes on this. The presentation here is slightly different than what I have in the notes, but it's essentially the same. It's not too much of a difference at all. Okay. Thank you very much. Have a great day.